In the previous class, we have discussed all about the Boyle-Savart's law. Okay, and in this class, we will study on the important concept magnetic field on the axis of a current carrying a circular coil. Okay, and now in this concept, the very important thing is what? Just you are going to find the magnetic field on the axis. Okay, and right now here, just to look at here in this figure, you will get it very easily. Right now, just I had considered this one is the circular coil or ring. Okay, and this is circular coil which is carrying the current. That is what I had done this one as the I. Okay, and now here the radius of this coil is A. Okay, and now here point P, what indicates that along this axis I am going to find the magnetic field. That is what here P. Okay. For example, if you want to look at the physical example means right now just assume that this is a circular coil, and right now here what I had taken on the axis means in the center point from this to here I am going to find the magnetic field at this point. Okay, and now this is what the circular coil. Okay, and now here this is what the point P, and now the distance from this DL to P is what here I had considered the R. Okay, and from this center of this point of the circular coil to the this point P is the distance is X. Okay, and in the similar way in the another part here I had considered distance in DL and P is the R here. Okay, and now here you need to know that what is this DL. In this circular coil I am going to consider only a small element. Okay, so it will be easier to get that what is the magnetic field along this axis. Okay, so after if you want to find the whole circular coil means at that moment just we need to integrate. Okay, so now here I had considered the small element, so that's why I had considered this one as the DL. In the similar way here also just I had considered the small element DL. Okay, and now here here as I said that this is the small element DL, and here also just I had considered the under portion DL. Okay, and now here right now I am going to use the important tool, which is I am going to find the magnetic field on this axis. Okay, so that is what the Boyle-Savart's law. So already we know that the Boyle-Savart's law, that is we can write that one as dB is equals to mu naught by 4 pi ideal sin theta by r square. This is what we know already. Okay, and now here just we need to find the angle here, that is what the theta. Here we are going to find the angle between the DL and R. How you are going to find the DL and R here? So but remember one thing, here the angle between not A and R, here the angle between what? DL and R. How you are going to find that one? Simply what we know that the direction of DL how you are having, this is the direction, this is the circular coil, and this is what the direction of this is the DL, is that right? And now here what is this, what is the direction of this R here up to this point P? Here you are having like this, is that right? So now if I had considered like this, just to look at here, what is the angle between this R and DL? This is what the DL, is that right? So right now if you are considered, just you rotate like this. So is there any changes with respect to that angle? Angle is what you are having. Angle between the DL and R is, that is angle between DL and R is always what you are having? 90 degrees. Okay, so now instead of this, if you are taking the other angle means what it will give you. Yeah, if I had considered like this means, so what it will give you, see, so if I can, this is 45, okay, 30, okay, so 20 degree, so like that if you are considered like this means it will be 90 degree. Okay, but with respect to the angle between this DL and R, it is always what you are having, it is 90 degree. Okay, so now with that reason I had considered theta is what you are having, this is 90 degree. So due to that reason, if you want to find the magnetic field at the point of P means dB at the point P, I can write this one as mu naught by 4 pi ideal sine 90 degree whole divided by r square. So already you know this is one, right? So now I can rewrite this one as mu naught by 4 pi ideal by r square. This is what we got dB after substituting the angle. Okay, and now here what we have to do here, simply after getting dB, I will go with the description towards this figure. What you are having here, what I had considered, what it will show you here, a dB, this is what the direction of dB cos theta. Okay, and now this is from the other side, it will be dB cos theta. Okay, and which is what? Which is the perpendicular to the axis. Is that right? And now here, with respect to that, what we are having here also, it will be dB sin theta. Is that right? And this here, the direction of this r, which is related to this dB sin theta, and in the similar way in this side, here it will be related to this point. Okay, you may consider like this. There are so many. You will get the direction of dB sin theta, and in the similar way here you will get the dB cos theta. Is that right? So in the similar way here, what we are getting that due to these dB cos theta, just to look at here, due to the opposite direction, this dB cos theta will be cancelled with each other. Those are vanishes. So that's why in the resultant way, I can write it here. Resultant manner, I can write the dB sin theta like this, because I had considered the sum over this dB sin theta. Okay, and now here what about the dB cos theta? It will be cancelled with each other. Is that right? And now here I can rewrite this one as integration over dB sin theta. Why? I am going to consider this one as the complete circular coil. Okay, so as I said earlier, I need to consider this one as the whole circular coil. If you want to find for that one means, I am going to consider this one as the whole closed integral, that is, I can write like this. This is dB sin theta. And now I can write this one as, already we know that what we are having the dB here, we are having mu naught by 4 pi into ideal by r square. So I can write mu naught by 4 pi ideal by r square into sin theta. What you are having, just to look at this figure, what you are getting sin theta here. What you are getting it here, simply you will get this one as the a by r. But r we can write this one as what? I can make out this one as the a square plus x square to the power 1 by 2. Okay, so now I can write it like this. This is a by a square plus x square to the power 1 by 2. Is that right? And now I can write that is b is equals to, just to take it outside all the constant parameters, mu naught by 4 pi. Okay, and now here I can write ideal by r square. Already we know that r is equals to what we are having, a square plus x square to the power 1 by 2. I can write that one as, it will be square is there, the square will be vanishes, and right now you are remaining with finally, that is a by a square plus x square to the power 3 by 2. Okay, and now here, so right now what I will do here, again I will make the integration over this. How you are going to write that one? That is mu naught by 4 pi I a by a square plus x square 3 by 2 into dl. Okay, and now this is, I can write this one as the 2 pi a, is that right? And from that b is equals to mu naught a by 4 pi a square plus x square to the power 3 by 2 into 2 pi a. Is that right? And now here, so here I can write this one as what it will gives you, 2 pi a into a square. And now here I can write this pi a square is what? This is the area. Is that right? And now that is equals to mu naught I into a whole divided by 4 pi a square plus x square to the power 3 by 2. Is that right? And now I can write this one as like this. So that is magnetic field B is equals to 2 mu naught I a by 4 pi a square plus x square to the power 3 by 2. Okay, and now this is what the final expression of the magnetic field on the axis of a current carrying the circular coil. Okay, and now here still I can modify this one as like this. I can write these two parameters by indicating one parameter, that is what, m. M what that will gives you? That will gives you magnetic dipole moment. Okay, so now here D is equals to, I can write this one as mu naught m by 2 pi a square plus x square to the power 3 by 2. What it will gives you? Magnetic dipole moment. Is that right? And now here this is what the final expression in the presence of magnetic dipole moment. And now here this B is, which is a dependent parameter of what here? Current and as well as the area here. Is that right? These are the dependent parameters here. Okay, if the current and it will be changes the area, means what will gives you? You will get the different magnetic field. Okay, so now this is what the final expression for the magnetic field on the axis of a current carrying circular coil. Okay, so this is what all about today's concept. Thank you.